Hi, everyone. We're continuing our series of lectures on the hydrogen atom in Atkins AA. Process for this problem is the same as every other one. We start by writing the Schrodinger equation. There it is. It has this ugly, gory form. We solve it, and I want to remind you that when you solve it, you get two things: wave functions and energies. Last week we talked about the wave functions. So they have two components, a radial wave function and the spherical harmonic, three quantum numbers, N, L, and M. Question is, what about the energies? And that's what I want to talk about in the next few videos. So here they are. And I am just giving you the form for these, the equation for the energies. There you go. It falls naturally out of the solution to the Schrodinger equation. It's the eigenvalue when you identify the eigenfunctions. And here's what you'll notice, right? Bunch of constants, 1 over n squared. Now, I actually don't have this memorized, but I do have this memorized. And the reason is that you'll see that this form of the energy equation has a bunch of common things in it. Specifically, a negative h bar squared over m distance squared. It might be L squared, it might be whatever. Remember that the quantum mechanical measure of distance is a Bohr radius, A naught. And so this looks exactly like you would expect for a quantum mechanical type system. Right? So negative 1/2 h bar squared over m A naught squared. Again, these are all constants, so you could plug them in and you could get some number in SI units. In SI units, they are equal to minus 2.2 times 10 to the minus 18 joules. Or more common yet, we convert this to EV, electron volts. And you might remember this from Gen Chem, the energies of hydrogen atoms are minus 13.6 EV over n squared. First thing we do, once we have an energy level, or once we have an energy equation, is to calculate the energy level diagram, to draw it. And here it is. So again, we're increasing energy. Right? One thing I would point out to you is that we now have negative numbers. So the lowest energy orbital is a 1s, n equals 1. It is at a negative value. As I increase the quantum number, this energy gets smaller. So the next one is n equals 2. There's a 2s, and there are 3 2p orbitals. There's 3s, there's 3p, there's 3d, blah, 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 blah. So let me point some things out to you about this equation or this energy level diagram that might be confusing. So the first is, this is our first system in which we have negative energies. Everything else had a positive energy. And maybe that's alarming, right? Should we be concerned? The answer is no. Remember that this system has potential energy. There's a Coulombic attraction between the electron and the nucleus. And so it's that potential energy which produces these negative total energies. We refer to these as bound states, right? We're measuring the energy of the system relative to an infinite separation of the electron and nucleus. If they were infinitely separated, they would have an energy of 0. We're looking at the energy relative to that. The second thing is, if I were to fill up my energy level diagram, hydrogen has 1 electron. So it's going to sit there. I could identify this quantity right here, right? Which would essentially be the energy which would be required to separate the electron from the nucleus. Qualitatively, you might recognize that description, the energy required to remove an electron. Well, that's the ionization energy. And because I know specifically what this value is, this lowest energy occurs at minus 13.6 EV, you can make a very simple theoretical prediction for what the ionization energy of hydrogen is. Run the experiment and compare these things. I will leave it to the worksheet to make that comparison, but what I can tell you is that it's very good, right? We can identify the ionization energy in hydrogen. One more thing. I told you at the very start that Bohr had made some unreasonable predictions or approximations. They led to a series of useful predictions, and specifically, he said that we should get hydrogen atom energies which obey this form. This explains some experimentally known data, and the Schrodinger equation now proves where this all comes from. So now we know the underlying physics and have a lot of confidence in what we're doing. A couple brain teasers. Which orbital is higher in energy, an S or a P? If you're anything like me, you're probably going to say a P orbital. P orbitals are higher in energy. But you have to think carefully about this in hydrogen. There's my energy level diagram. In hydrogen, the S and P orbitals are degenerate. The energy only depends on N. And this has a number of important consequences. So, for example, which orbital is larger, an S or a P? Well, if you're anything like me, you say a P orbital is bigger. But now you process that. In terms of their angular momentum, a P orbital has more angular momentum than an S orbital. L is equal to 1 in a P, L is equal to 0 in an S orbital, right? So the P has more angular momentum. If it has more angular momentum, it has to have more kinetic energy. If it has more kinetic and the total energy is the same, that means that the potential energy in a P orbital is smaller than the potential energy in an S orbital. How do you reduce the potential energy of an electron attracted to a nucleus? You bring them closer together. I think of it like a spring. If I stretch the spring, the energy goes up. If I bring it closer, the energy goes down. So in fact, in hydrogen, a P orbital is smaller. And I tell people this and no one ever believes me. So here are these radial density plots. And what you might be able to see there is I outlined in red where the most probable radii are in the S orbitals. If I overlay those on the P orbitals, you can see it actually pretty clearly in this 3P orbital. The P's are inside of the S. Right? Really is true. And on the homework, you are going to mathematically show that the 2P most probable radius is less than the 2S. One last teaser. In the ground state of a hydrogen atom, is the kinetic energy of the electron 0 or not 0? In other words, is the electron moving or is it not moving? And the answer is it's moving. It's not 0, right? It has some kinetic energy there. In the ground state of a hydrogen atom, what does every single measurement of the angular momentum return? Well, remember that the magnitude of angular momentum is determined by L. The specific equation is absolute value of J equals L times L plus 1 to the 1/2 times h bar. I have an S orbital, L is equal to 0. And that means it has no angular momentum. So can you explain these two? It has kinetic energy, it is moving, but it has no angular momentum. I would love to hear your explanation. I will stop there. I hope that might pique your interest a little bit. I have one more brief video for you, and I will see you then.